All right, guys, we are on our final rule for differentiation. It's called the quotient rule. I posted this worksheet. It says blank quotient rule notes on Google Classroom, so you could print out or just copy. It's just 3 examples. And basically the rule is given to you. And it looks super familiar because if you look at the order, the way that we would read this is the derivative of some quotient, right, of some function that I can identify as a quotient. The top I'm going to call f of x, and the bottom I'm going to call g of x. But you'll also refer to me as the top being the first function and the bottom being the second. That being said, if you look at our rule, this is just saying that the quotient rule is equal to the derivative of the first, which is f prime of x, times the second, not taking the derivative, minus the derivative of the second times the first, and the extra piece is all over the second squared. So the only thing that this has changed from product rule is that the plus turned into minus, and the bottom is now added with the second function squared. The big thing that you should remember when doing this, because it definitely looks more complicated, is that you should have brackets around the first term and the second term. So if you were to be given this yesterday before you learned the quotient rule, you might have said, oh, I'm going to rewrite this as y equals x squared plus 1, and then you could have brought up this bottom. And when you bring up any term up, we have to use a negative exponent, and now I would have this. So technically, you could do this problem with the product rule, except now it's the product rule with a chain rule combined. This does not make my life easier, so that therefore I would go and prefer to use the quotient rule. When should we use the quotient rule? Because I like to avoid this as much as possible. The quotient rule should be used when you have a variable in the numerator and if you have a variable in the denominator and you cannot simplify. So what do I mean by that? My 4th example today, which is not on your worksheet, I will explain a little bit further, but if you have a binomial divided by another polynomial, something greater than a monomial, where you can't just divide it into each term, well then you're going to want to use the quotient rule, because this is not any easier than this. So I'm going to cross this out, and I'm going to make my key like I've been making. I'm going to recognize that the top is what I consider f of x, or my first function, and the bottom is what I consider my g of x, my second function. So off to the side, I'm making my key. F of x, the first function, is x squared plus 1. The derivative of the first function is 2x. Then g of x, we just said, was 2x plus 3. And the derivative of that is 2. So now I have all the pieces I need. I'm ready to go in and take the derivative. I always like to write, especially in the very beginning, the rule. And so the derivative is the derivative of the first times the second minus the derivative of the second times the first all over the second function squared. Okay, so I like for you to kind of say that out loud to yourself a couple of times, and just that's how you keep it memorized in your head what the steps are. And we purposely rewrote the product rule in this form because addition's commutative. If you study the product rule, the quotient rule in a calculus textbook, the product rule will actually be reversed. But to me, that's more confusing to learn new orders. So I just kept the order the same. But I don't want you to, in the future, go, I didn't learn it that way. I learned it different. It's fine, because in the product rule, if I took this term and put it in front and this term and put it at the back, and it's an addition, it doesn't make a difference. But in quotient rule, it absolutely makes a difference. So we know that subtraction is not commutative. This order has to be in this form. Okay, so let's go ahead and find the derivative. dy dx is equal to the derivative of the first is right here, so I just put in 2x. And then times the second is 2x plus 3 minus, and then I like to give myself a little bracket there knowing that that's one term. And then another bracket to start the second piece. The derivative of the second is just 2 times the first is x squared plus 1 all over the second squared. So we're going to put here the second's 2x plus 3, and that is being squared. So now that's really it. You just have to clean it up. You look inside this red bracket, and I can distribute this because this is a binomial raised to the first power. So in here I get dy dx is equal to, and in the first bracket I get 4x squared plus 6x. And in the second bracket, I'm able to distribute this 2. And you get 2x squared plus 2 all over the second function squared. This piece I don't expand, but I do continue to now distribute that negative. And then that becomes 4x squared plus 6x. Nothing happens. I'm distributing a positive one in there. This becomes negative 2x squared minus 2 all over 2x plus 3 squared. So last but not least, let's combine like terms in the numerator. I got 4x squared and negative 2x squared. That gives me a positive 2x squared. There's nothing to combine with 6x, so that stays positive 6x minus 2 over 2x plus 3 squared. Now, we're done. If you see that this is a trinomial that can be factored, I could try to factor it. 2 times 2 is negative 4. What are the factors of negative 4 that are going to add up to 6? That's not going to happen, so there's nothing more to simplify. This is my answer. All right, let's look at the next example. The next example gives me this. So at this moment, I would suggest for you to pause the video and go ahead and make your key and try it yourself. So f of x is the top, what I call the first equation, x cubed plus 1. Therefore, f prime of x is equal to 3x squared. G of x is x squared plus x. G prime of x is 2x plus 1. Okay, so now f prime of x, that's the derivative of this function. So when I have that, I can write the f prime, and you know that this does not refer to this, the derivative of this. So I'm just going to write the derivative of the first times the second minus the derivative of the second times the first all over the second squared. Okay, so we can use our key, or as you'll see next year, you're really going to just be doing this so often that it'll just come natural and you can do it as you're working this out in your head. So the derivative of the first is 3x squared times the second, which is x squared plus x, and that goes in my first bracket, minus the derivative of the second, which we just said was 2x plus 1, times the first, which is x cubed plus 1, all over the second squared, x squared plus x squared. Okay, and you always want to take a look at that key and say, okay, derivative of the first times the second. Make sure that you don't accidentally pick the wrong equation to plug in. And last but not least, you want to distribute. So you're going to get 3x to the fourth plus 3x cubed minus, here, this one's a little bit of a pain because you have to double distribute, but that's okay. So we get 2x to the fourth plus 2x plus 1x cubed plus 1 all over that second squared. And I've had kids in the past that just clean up the numerator first and then worry about putting the denominator squared last. That's fine, but I will say some kids forget, and then there's a lot of mistakes there. So let's just continue cleaning this up. There's nothing to do in here. It's 3x to the fourth plus 3x cubed minus here. I can't combine anything either, so I can drop these parentheses because I'm distributing that one here. Here I'm going to distribute the negative. So that becomes negative 2x to the fourth. I'm just going to put this in order. Minus x cubed minus 2x minus 1 all over x squared plus x squared. And then I just combine. So here I can combine a 3x to the fourth and a negative 2x to the fourth to give me 1x to the fourth. 3x, positive 3x cubed and negative x cubed is positive 2x cubed minus 2x minus 1 all over x squared plus x squared. And that is my final answer. Again, you could see if you would be able to GCF this out by grouping, and I would not have a grouping scenario that would clean this up and simplify in any way, so I leave my answer like that. Okay, moving on to our third example. So our third example is also warrants a quotient rule because there's a variable in the numerator and a variable in the denominator. Now, I just want to make note, here I have to use the quotient rule because I cannot take this and divide it into this. But this problem, which you do not have, I'm just showing you in this case, you wouldn't use the quotient rule. I could rewrite this as x cubed over 2 over x to the 1/2. And then that is equivalent to x cubed over x to the 1/2. If you're dividing by a monomial, you absolutely want to go ahead and rewrite the original function, not taking the derivative, and simplify it. So this 3x to the third divided by x to the 1/2, we just subtract that. We get x to the 2/5, which is 5/2, plus 2 over x to the 1/2. And then I would bring this up by using a negative exponent. And what I just did was rewrote f of x in a form that I can just do the simple power rule here. Okay, that's possible because I was taking a numerator that has a variable and a denominator that has a variable. But since the denominator was a monomial, I want you to divide that into each term and avoid using the quotient rule. This will make life a lot easier. And I can't tell you, a lot of kids miss this, all right? And what happens is they go and do a lot more work, and it's a lot more complicated. So if you ever have a variable in the denominator and it's just a monomial, then you can just go ahead and divide it into the numerator, into every term, and rewrite that function so that you have a polynomial and you can do the basic power rule. In this case, we couldn't. I can tell right now that I'm going to get cut off, so I'm going to stop right now with this video, and I'm going to take another video finishing this example. So I'm going to hit pause right now.